Hello, lazy chemists, and welcome to today's lecture where we are going to be going over the concept of stoichiometry, and we're going to go ahead and start doing the formal concept in terms of the numbers and everything here. And this is going to be kind of like a keystone point lecture for us, where a lot of the chemical processes that we're going to use in the future are going to be extremely dependent upon this linchpin of stoichiometry. Now, stoichiometry in and of itself is a Greek term for measuring the elements. And this is how we measure the elements that are in a chemical reaction. And as it's defined, like we need to be able to use a balanced chemical reaction in order to solve this one here. And there's going to be 4 different ways that we can measure elements here going forward. The first is going to be in terms of moles. The second is going to be in terms of mass. The third is going to be in terms of particles. And the fourth is going to be in terms of volume, okay? And I would like to add here, and we're going to add one more to this one here. And it's going to go ahead and be concentration. It's going to be our last one. And concentration, again, that's going to end up being moles over liters, okay? And these are the 4 ways that we're going to be able to interpret a chemical equation. And some of these are going to be more important than others. So for instance, it's really difficult for us to actually count the number of moles in a compound in a reaction, but it's really easy for us to go ahead and measure mass. It's impossible, just absolutely impossible for us to measure particles, but volume is something that we're able to do quite easily. In fact, chemistry was really discovered through the use of volume back in the 1800s. And the last one is going to be concentration. And concentration is another useful one that we'll be able to tell what the concentration of different products are and therefore their moles fairly easily, because we're going to make different concentrations, and usually we use that using mass and some volume of liquid. Okay. The most common, easy factor that we are going to use is going to be the mole ratio. Okay, and this is what we essentially are making those coefficients for. So in this reaction here, what we have is we have 2 moles of aluminum oxide coming together with 4 moles of aluminum to make 3 moles of, or actually it breaks down to 4 moles of aluminum and 3 moles of aluminum oxide. Okay, and this is why we've kind of made this balanced equation, is so that we can compare the number of each particle to each other. Okay. And this ratio of aluminum oxide to aluminum is what's going to be known as our molar ratio. And it's a key part of each stoichiometry equation because it tells us how to get from one substance to another. So it says, like, if we have this much aluminum, aluminum oxide, we can end up getting twice as much aluminum because, look, that ratio is twice as big. 4 is twice as big as 2. Okay. So these are the things that you'll want for like a definition for these. That's the ratio between 2 substances in a balanced equation. And we derive that from the balanced equation, namely from the coefficients in the balanced equation. Okay? And our mole ratios, how we're going to do this is I'm going to offer you 2 methods here for doing this here. The formal way, the way that most of your college professors are going to want you to write it, is going to be 4 moles of Fe and 3 moles of O2. 3 moles of O2, 4 moles of Fe. Okay? However, I know also for myself in my class here, I have for years gotten rid of this mole because I just understand that it's a mole. So if you end up writing it with mole, yes, that is correct. If you write it without mole, that will also be correct. Because the fact of the matter is that when we end up going through this equation here and we mess through it, these two moles are going to cancel out anyway. So that's the lazy chemist in me not wanting you to write quite as much. Both ways will be correct, but realistically, in this equation here, what this is stating is that 4 moles of iron and 3 moles of O2, and this is a molar ratio. Okay, iron is present with oxygen at a rate of 4 to 3. Iron and iron oxide is at a rate of 4 to 2. Okay, and that's essentially what's going on with the molar ratio here. It's just stating how quickly or not how quickly. That's reaction rates. That's a different beast. It's stating how much of one substance can be made from another substance, and likewise. Okay. And this is just another example using O2 and Fe2O3. Okay. And whenever we're going to use this, we're going to go ahead and use the mole ratios. And it doesn't really matter which one goes on top. They're all ratios of each other. The reason that we have both of them here is because what's going to happen often is whatever compound that we're going to start our equation with, we're going to make sure that the mole ratio for that ends up being at the bottom. So any question that states that we have 32 moles of O2, well, automatically we're going to be like, oh, okay, well, we have O2, and that's what we're going to want to get rid of, okay? And this is just using simple dimensional analysis here to go ahead and, get rid of different, essentially, units that we don't want to have at the end of our problem, okay? So let's go ahead and start with this one. And it's going to say how many moles of O2 are produced when 3.34 moles of Al2O3 decompose. Okay? So our first step, we're going to need to write down what we have. Okay? This is kind of like our mole conversion problems here. Alright? And we have 3.34 moles of Al2O3. Now we're going to have to ask the question, what thing do we want to get rid of? Okay, and the thing that we're going to want to get rid of, we're going to use the mole ratio where that one's at the bottom. In this case, we were given aluminum oxide, Al2O3, so we're going to want to make sure that that one ends up on the bottom. Okay, and we have 2 moles of aluminum oxide for every 3 moles of oxygen. Okay. And then from here, all that we'd have to do is multiply the 3.34 times 3 and then divide it by 2. And that'll give us 5.01 moles of oxygen. Okay. And if we wanted to, and go ahead and suppose then we would go and say like, well, what about the aluminum now? Well, to be perfectly honest, all that I would do for the aluminum one is I would end up crossing this one out and I'd put 4Al on top. And it's the same equation going forward, okay? So a couple of things that you're going to need to remember for this one. Whenever you go through this one, you're going to have to make sure you have a balanced equation. You're going to use the mole ratios. And then you're also going to want to make sure that you're double checking with your units. To be honest, you're going to want to make sure that you're using your units to solve most of these problems, because then you don't have to think as much. And let's face it, thinking isn't really for the lazy chemist. We'd prefer to just, set up our units and then have it go forward that way. Okay, Next is a conversion using mass, okay? So, oh, okay. Just a second, I had to review my notes for this one here. Okay. Now, mass, we can go ahead and what this slide is here talking about is that it wants us to go ahead and double check, you know, that mass of products equals mass of products on the other side. Okay, so here we have 2 units of hydrogen gas, 1 unit of oxygen, and we make 2 units of water. So we have 2 moles of hydrogen gas times the mass of hydrogen gas, okay, and this is the molar mass of hydrogen gas. Okay, it's 2.02 because each hydrogen has, you know, 1.008, and then you add them together, and we're going to end up getting essentially this here, plus 1 mole of oxygen gas, and oxygen is going to be 32 grams, which means that on the left side we have a total of 36.04 grams of H2. Okay. Now here we have 2 moles of H2O. Okay. H2O weighs 18.06, which happens to be the same as our original, which times 2 moles of it equals the same as our original, the stuff that's on the left. Which means that the mass that we put into it is the same amount of mass that we put out of it. Which is good because remember, you know, mass has a lot of energy, so if we accidentally destroyed some, we'd be in quite a pickle. Okay, now this is where we're going to be using our mole hole diagram. Okay, often what will happen is that we are going to be given or will be able to measure a stoichiometric calculation using mass. And we'll have to go from mass to mole, and then we'll have to go and convert from mole to mole, which we've already done. And then usually from there we'll have to either go to mass or to volume, okay? And these are our fairly typical ones that we'll have to do. The most common one is mass, because often we have to weigh out our chemicals before we put them into something. Then we'll go ahead, and this last one here, this is particles. I'm going to be perfectly honest with you, particles, absolute garbage. Absolute garbage. Nobody goes through particles. Okay. So, these are the 2 that we're going to be really concerned with, as well as working with some solutions. But we're going to be working with those slowly and throughout the year here. So, these are our general rules. We're going to balance equations, convert the starting amount to moles, use our conversion factor as a mole to mole factor, and then we're going to convert moles of the to desired unit, whether it's going to be 2 grams or if it's going to be to concentration or if it's going to be to volume. Okay, so for instance, this one here, we're going to go ahead and say that we have 0.400 moles. All right, so this problem, oh, come on, there we go. We have 0.0400 moles of iron, okay? We're going to go ahead and get rid of, from this equation, we're going to have to get rid of iron, because we're in moles. So once we're in moles, that means that we can automatically use our mole ratio. So we're going to use our mole ratio, and we're going to go ahead and get rid of iron, okay? And from there, we're going to be able to say, all right, well, how many grams of O2? Well, in order for us to go 2 grams, first we have to go to moles of O2. So we're going to make a ratio that goes from 2 moles of iron that we're getting rid of to 3 moles of O2, okay? And we want to get rid of iron, so we're going to put that on the bottom. 3O2 will be on top. The last step that we're going to do is we're going to go ahead and convert it from moles to grams. And this is something that we've been practicing for like the last week or so. It's going from moles to grams. So we're going to go ahead and have moles on the bottom and then grams on top. So our equation will end up looking like this, where here we have 0.40 moles of Fe2O3. Okay, and that gets canceled out. We'll have 3 moles of O2 here. And 1 mole of O2 equals 31.998 grams. Okay, when we do our math, we're just going to go ahead and use 32. And then that'll give us our amount in grams of oxygen. Okay. The next one that we're going to go ahead and do is say that we produce 13.1 grams of water. How many grams of O2 was reacted? Okay. And it's going to be the same way. We're going to start with 13.1 grams of water. We're going to use the balance equation here. We're going to use the balanced equation here. It's in grams, and we need to get it 2 moles, so we're going to go ahead and go grams over moles. Then we're going to convert from water, and we have 2 waters for every 2 moles of water, for every 1 mole of oxygen. So we're going to indicate that, and we're going to get rid of water. Okay, so water will be on the bottom, oxygen will be on top. And then our last step is to go from moles of O2 to grams of O2. So we're going to put grams on top, because that's what we're looking for. And then moles of O2 on the bottom. Okay, and that's the basic way for going ahead and solving all of these problems that use that particular grams to grams method. And what I like to phrase this as is that we have essentially created a system where we have 3 conversions here. Okay, we have a conversion to get to moles. Then we have a conversion where we go ahead and convert to the element or compound. And then we have a way to convert out of moles. Okay. And so this is another thing that might help some of you out here, that if you have one where it's get to moles, you'll want to make sure that you have moles on top. Then you'll have a conversion where you go ahead and convert from your original element to the element or compound that you want to end with. And then you'll have a conversion out of moles, where moles will typically be on the bottom. The only exceptions to this rule, this general process, is going to be if you're working with solutions, in which case you'll have liters kind of replace moles because you've already started with a molar volume. Okay. So this is just a general reminder that in general for this one, a mass to mass, you're going to go from mass to moles, from moles given to moles desired, and then from moles desired to grams desired. Okay. Now next we're going to go ahead and say that we're doing one that's pure volume. Okay. And remember that 1 mole of a gas is going to equal 22.4 liters. Okay, so that means that if we have 2 moles of hydrogen gas coming together with 1 mole of oxygen to make 2 moles of water, we would have essentially 44.8 liters of hydrogen coming together with 22.4 liters of oxygen to make 44.8 liters of H2O. Okay. So this one, we can go ahead and, think this through just the same way that we have been before. Okay. Here we have liters. If we want to go ahead and go from liters from O2 to CH4, we're going to have to first get it into moles. Alright, so to do that, we'd have to divide by liters, and 22.4 liters equals 1 mole. So we have this conversion factor here, okay? And now we're in moles. So this is exactly like the gram scenario, except that we have liters. And in fact, volume to volume is a little easier because you always know that it's 22.4. Then we'll convert moles of O2 to CH4. Okay, so 2 moles of O2, 1 mole of CH4. The last thing that we're going to do is we're going to go ahead and be like, hey, we're not interested in moles of CH4. We need to get our desired unit. We're looking for liters of CH4. So we'll have to put liters at CH4. Now, from here, we have our liters. But I want you to take note of something. Okay? Some of you, your inner tingling is happening in your brain. You're thinking, Mr. Bradley, is there a way? Is there a way to make this lazier? And I can tell you that there is. And some of you have already figured it out. But here, our liters, here and here, they would have canceled out. Which means if we're really lucky and we get a volume to volume measurement, our liters automatically cancel out and we can go ahead and get rid of that extra step right there. Okay? So just be aware and on the lookout for that. If you are uncomfortable doing like the super lazy way, if you do it the standard way, that's always going to work out. But if you do see that you have 22.4 liters and it's on both sides, you could just cancel that out right away and you should have no real issues. Okay, and this is just the reasoning behind it, that equal volumes of gas at the same temperature and pressure all contain the same number of particles. Really revolutionized chemistry as a whole science, to be honest. Okay, and this right here is just showing you the shortcut method. And if you did this math, you'd be able to be like, oh yeah, that is how that works. 17.5 divided by 2. Okay, so just a quick reminder, this is the technical way for how things are supposed to be going with this, and we just have shortcuts that we can use in between here. Okay, this is going to go ahead and close us out for the main stoichiometry portion. This section is going to take a little bit of practice. I expect that you guys should need a good amount of practice, and you're going to need to ask questions here, and that's perfectly fine. The worksheets that we're going to end up giving for this section, anyone that I give answers, I'm going to want to see your entire process, but it's going to be one that you'll be able to check your answers for at least a couple of the worksheets going forward. But for now, I want you to go ahead and just take the time to go ahead and finish up your worksheet. And remember to stay lazy.